All right, welcome everyone. Thanks for being here. Really thrilled to have Kyle Dawson visiting us today. Kyle is a faculty member of the University of Utah. And he's been working on spectroscopic surveys for a long time. I think he started at Berkeley with, where he did his PhD working on the Sloan Digital Sky Survey and BOSS. He's been a spokesperson of the DESI experiment, which is a very large 500+ person collaboration. I had the pleasure of leading that collaboration before we had data. And helping get it approved, but Kyle has been really in the thick of things with these extremely exciting cosmology results, and he's going to tell us about the first ones, but as you will, I'm sure we'll also hear, there's a lot more to come after that. So thanks so much for joining us, Kyle, and look forward to it.
Okay, so, great, thanks, Risa. So that mic was pretty loud. How is my voice right now?
Perfect.
It's okay? Okay. I feel like I can control my pace better if I don't have the mic. Okay, so I'm going to talk about the first year cosmology measurements from DESI. DESI is the Dark Energy Spectroscopic Instrument. It is the successor to a project that ran for a long time. Many of you know it's the Sloan Digital Sky Survey. I'll give you a little context there. I'm going to give this talk in parts, and I'll take questions at each stopping point. But I'm also, of course, always happy to take questions along the way. I actually find it much more interesting from my perspective to be interrupted. So please go ahead. I'll keep an eye out for people raising their hands and pipe up and make a sound if I don't notice. So moving into this, so as Risa mentioned, DESI is a very large project. It's a collaboration of many hundreds of people. We often say 1,000, although the exact number is very ambiguous. Not everyone works the same thing every day. And it's about 72 institutions sponsored by the Department of Energy. So I'm going to start with a little bit of the background on cosmology. I believe there's a wide range of the audience, so I'm going to go to some in 10 slides, cover the basic principles, and then get into data. So starting with spectroscopic surveys and cosmology, the basic idea here is we want to measure the fundamental properties of the cosmos by measuring the time evolution of matter and how matter is distributed in the cosmos. Here's a classic example of a dark matter simulation, and you can see filamentary structure. We measure how that evolves with time, and from doing so, we can get at the physics of dark energy. We can get at the composition of the universe, neutrino mass, inflation, laws of gravity, etc. And the basic model that we have for cosmology based on measurements up till, like, let's say from 1999 to 2020 before DESI started, the universe is something like 70% this dark energy component. Dark energy leads to an expansion of space that's accelerating in more recent times. About 25% dark matter, about 5% we call baryonic matter. On this chart it's called atomic matter. And then there's relics. In addition, we can actually see the signature in cosmology from both photons and neutrinos in multiple ways. Okay? So we actually have pretty good constraints on both of those parameters as well. Okay? So the technique we use, primarily what motivated the design of the DESI program, is called the Baryon acoustic oscillation technique. Baryon acoustic oscillations are a way to access the Friedmann equation. The Friedmann equation is here on the right-hand side. It basically describes the equation of motion for the expansion of the universe. So the expansion term is this h on the left, and on the right is the terms that drive that expansion. It's basically what is the universe made out of. So we can get different measurements of that h or some integral on h. We can start constraining what's on the right-hand side of the equation, which is what we care about. What are the physics that drive that? And the technique we use in this artistic rendition that I think is both fantastic and super misleading is the clustering of matter has a preferred scale where you're more likely to find extra matter to separations about 150 megaparsec, about 500 million light years from any point in the universe where there's matter. So you look at the correlation function, And here at the center of each of these rings is an overdensity of matter denoted by galaxies, a lot of galaxies. You got 150 megaparsec in any of 3 dimensions. Here it's just shown as a slice. But you go out in any 3 dimensions and you see an excess probability of galaxies. But to tease that out, you can't just look by naked eye. You can't look at something so clearly as this. You need millions of galaxies to tease it out statistically. Okay? If you can tease that signal out, it gives you a standard ruler. And once you have anything in the cosmos where you can get a distance measurement, a standard ruler, a standard candle, or whatever, then you can start measuring that left-hand side of this Friedmann equation. And if you can measure it at multiple epochs, you can start deriving how it changed with time and what the universe is made out of. So what specifically is the standard ruler? Again, it's the Baryon acoustic oscillation, or BAO feature. It's imprinted in the first 300,000 years of the cosmic history. What's shown here on the left is the initial imprint of that signature. It happens at the very early times when inflation ends. And imagine if you have a fluid like baryons and photons. If you perturb that fluid, a pressure wave travels outward. It travels outward at the sound speed, and it travels outward until it freezes. So here is the initial perturbation and that pressure wave traveling outward. It freezes at 300,000 years when the photons and the atomic matter, the baryons, are no longer coupled to each other. They're no longer talking. And it's permanently embedded in the baryon distribution. So that's what we see in the galaxies. That's what's shown here in the middle panel, the same figure I showed before. It's not as simple because it's not a single perturbation with a high density. It's actually many perturbations superimposed on top of each other, so you have to tease it out statistically. That's what's actually shown more accurately here in the bottom left. Here's my telescope looking out in the cosmos. I can see this distribution. This is kind of an important detail, but I can see it in 2 different dimensions. Parallel to the line of sight, that's looking up. That's the DH term. So if I can measure that separation D in the parallel line of sight, I can basically measure directly that Hubble parameter, that H term. And the other is DM. That's that's perpendicular to the line of sight. There I can make angular diameter distances measurements. So I can measure, I know what the physical scale is of this feature. I measure the angle it subtends in the sky, and I get a distance to that point. And once I have these distances, I can get my Hubble parameter, my Friedmann equation. Okay? What it looks like statistically, when I have hundreds of thousands or millions of galaxies, is shown here in the correlation function. We can do this in 2 different planes, configuration space or Fourier space. I find it much more intuitive in this plane here where it's configuration space. You can see this on the y-axis represents the expectation above average, above random for finding 2 objects separated by a certain distance. So the probability beyond random that I have 2 galaxies at a preferred separation. And you can see, as I get to larger and larger separations, the probability declines up until I get to that really special scale, and I see that boost in probability. That's my preferred feature. That has a fixed scale at all time because this feature gets imprinted at 300,000 years after the Big Bang. Okay? So that's the basic idea.
Is that just theory that this feature becomes frozen in, or do you actually have data that shows that you don't have evolution of this one correlation function after a certain point of history?
Okay, so the question is it theory that leads to this prediction that it's frozen time, or is there data that strongly confirms it? So the theory is pretty sound. We have a very good model for how baryons and photons couple each other in the early part of the universe, and that model is very, very well constrained by the cosmic microwave background. So it is from theory, however, all the predictions are confirmed to very high precision. And it really just comes down to knowing the densities and temperatures. Those are the 2 primary terms that determine, that set when it separates. The relative density of photons, which is very, very well known, relative density of baryons, which actually doesn't make as much of a difference, and then the current temperature of the CMB. And then from there you can figure this out. So we do now, once the theory is established and the CMB help confirm it, we treat this as a standard ruler. We're trying to measure the distances as a function of redshift. What's the Hubble diagram? much like you see in a supernova Hubble diagram. And we're specifically trying to measure what's the properties of dark energy beyond its total energy content. How is that energy content evolving with time, or what's its equation of state compared to what the standard model is, which is cosmological constant. So I think this is a really nice conceptual design of the Hubble diagram. This is all normalized to our standard cosmological model, where this dark energy term is the cosmological constant that comes out of Einstein's theory of relativity, general relativity. And what we're looking for is changes relative to that lambda CDM model to see if it really is that explanation for dark energy. Here is one parameterization that's very simple that says, let's allow the equation state not to be what Einstein predicts, but off by plus or minus 10%. And constant in all time. The red is below 10%, the blue is plus 10%. You can see those two terms, the DM term and the DH term, that I can measure with my BAO feature. Out over the redshift range, for which DESI is sensitive, redshift 0 to 2.5, I'm basically looking for changes in the order of 2.5%. And I'll tell you something, it's a very small effect. We're actually constraining this term at about 3%. So this is a 10% fluctuation. This is a much bigger shift in the amplitude than what we're able to measure in the data. Okay. So we're not just interested about a constant equation of state. There's a lot of theoretical models that say once you get away from Einstein's theory of general relativity and accept other descriptions of this dark energy, that they must evolve with time. The equation of state must evolve with time. So we have a very simple parameterization that allows for that. And in the simple parameterization, it's basically a linear form that evolves on redshift, which is effectively this A term.
I can't see because I don't have my glasses. Is the vertical axis W?
Okay, so the question is, what's on the vertical axis and what's on the x-axis? A great question. The x-axis is redshift or distance. The vertical axis is distance. So it's the distance that I'm measuring with the BAO feature, so the distance to that redshift. But it's normalized to my standard model. Now the color scale,
Model mean W equals -1?
the standard model means W equals -1 today, yesterday, and for all of time. That's right, exactly. So that last one was perturbations, where it was constant and not equal to -1. Here is now where it's evolving with time and not equal to -1. And these are plus or minus 40. 0.4, and again, 2.5% discrepancies. That's kind of the level at which we need to make these measurements. Okay. Okay. Now, there's a long history before we got to DESI, starting with supernova, moving to the longitudinal sky survey, which really introduced this technique with Baryon acoustic oscillations as a way of measuring the Hubble diagram. I think this is informative for two reasons. First, I really love showing the scale at which this experiment happened. There was 4 different stages from 2000 all the way through 2020. In those 4 stages, we measured about 4 million redshifts of galaxies and quasars in 20 years, 2 decades. And we got a Hubble diagram. It looks just like that figure I showed before. This is now the same axis, distance on the y-axis, redshift on the x-axis, but I have real data points from that 20-year experiment with error bars. And you can see them scattering up and down about the cosmological model, about the standard model. And you can see the real precision at which we're measuring this BAO feature. Those are real correlation functions from each of those individual samples. So we can divide up our galaxies into different redshift bins, and each redshift bin measure directly this BAO feature and get a distance as a function of redshift. Okay? And you can see the level of precision varies. Some of them are beautiful measurements, some of them are a little cruddy. It all depends on the quality of the data and how the telescope and survey were optimized for that data sample. Okay, but 4 million galaxies and quasars in 20 years. What did we learn at the end of that project? This is the summary of all cosmology constraints from those 20 years of data. The model I'm showing here allowed 3 free parameters to vary beyond the lambda CDM standard cosmological model. The first is curvature. The second is that equation of state for dark energy characterized by the term evaluated today, W or W naught, and WA, which tells you the linear evolving component of the equation of state. So the standard model would be 0 curvature, W equals -1, WA equals 0, meaning it's not evolving with time, all denoted by these hash marks and where they intersect in the in all the planes. What's interesting is the curvature component, no matter what we did, we found was consistent with 0. I'll show that, I think I'll show that later if we see the same thing in DESI. In the WWA plane, when I combine all the samples that were available in 2020, I see the gray contours. That gray contour represents the best constraints we had at the time, just 4 years ago, based on our CMB observations, cosmological background, our BAO measurements from the Celestial Sky Survey, and from supernova, which at the time was a project that was called Pantheon. And that was the best supernova sample at the time. And this gray sits in the bottom right-hand corner of this plane. It has a preference for W naught being greater than -1, so to the right of the vertical line, and WA less than 0 to the bottom of the horizontal line. And it was about a 2 sigma discrepancy. So 2 sigma, anyone has seen many 2 sigma fluctuations, is not exciting. We didn't think anything of it. All we did when we wrote our summary result was report the precision at which we were able to make this measurement. What were the size of our error bars? We said, everything looks like lambda CDM. Look how great we did with our small error bars. That was the summary of this paper we wrote in 2020. Okay? But I want to kind of remind you that before we started DESI, there was a mild preference for sitting in this bottom right-hand quadrant of this parameter space. Okay? Okay, so that's some background. I see a clock, I'm on good time. Are there any questions before I go to the DESI data?
What were the histogram-looking things on the previous plot on the diagonal of this?
So here, here, and here?
Yeah.
Okay, great question. So for each, this is a corner plot, and each place where I have 2 dimensions, I have this parameter against this parameter, I can see a 2D contour. When I go over here, I only have 1 parameter, so it's the 1D posterior on that parameter. So this is the 1D constraint on the WA term, and in gray is our best data with all data samples. And it was different from 0 at about, let's say, a little more than 1 sigma in that 1 parameter. The same thing for W naught and the same thing for curvature. But it's basically the 1D posterior on each of the individual parameters. I find a lot of these cases, especially with this time evolving equation state, I find this particular presentation to be the most informative because you can really see with these really, I mean, you can see it's really degenerate. There's a diagonal component there. You can really see how it syncs up as a whole relative to the lambda CDM model. So I prefer that plane. Okay. Okay. So I'm going to spend a little more time talking about cosmology from DESI than I just showed from Sloan. I'm going to give you some overview of what we did in the DESI measurements. I'll probably try to go through this quickly unless you have questions. But here I'm basically going to show what DESI is, how it was so much better, been so much better than Sloan, and just justify how careful we were in the analysis, but very, very quickly, okay? But if we want questions, I'm happy to stop and take questions. So first of all, the Celestial Sky Survey was in New Mexico. DESI is in Arizona. That's one change. DESI is a 4-meter telescope, whereas the previous project was 2.5 meters. So you get a lot faster light collection. And overall, the goal of DESI here is to make the most precise measurements of this Baryon acoustic oscillation feature possible. And we specifically set ourselves with a goal of making those confidence intervals I showed you on the last slide, that W naught W plane, 10 times smaller in area than they were at the time DESI started its design phase. That was around 2010, actually. So it takes a long time to build these experiments. So even though we had a decade of progress, we were setting our requirements based on the 2010 measurements, ignoring what was going to happen. So that was the primary driver. DESI does a lot more than BAO. If we have time at the end, we can talk about some of that. I suspect we will not. But I'm just going to focus on this one dimension of the project. Okay. Make the measurements of the precision that are required to get that error bar down by a factor of 10 in that 2D space. we need a lot of galaxies and a lot of quasars. And specifically, we want to have uninterrupted coverage between redshift 0 and redshift 3.5. Redshift 3.5 is about 12 billion years in the past to calibrate your translation of redshift to time, okay? And of course, redshift 0 is today. So we get 12 billion years of history. The sum over all these different classes is about 40 million galaxies and quasars. So about 10 times bigger data sample size than what we did in Sloan. It's a detail, but based on the redshift range, the number density, we have to change the way we select galaxies for redshifts. So that's why we have these different color patterns in black, red, purple, and green. That's just representing different selection scenarios for how the objects are detected and actually how they're redshifted as well in the spectrograph. So one of the key things that allows us to operate, yeah, go ahead, please.
Yeah, if you can go to the previous slide, why for physics you have like structures?
Yes, okay. So I was going to get to that in a little bit, but it's a totally excellent question. So notice how I have just dots for the galaxies and the black, the purple, etc. But when I get to the green, the quasars, I now have what look like these skewers, and they're color-coded like barcode along the skewer. So what that is a different measurement we make of those redshifts, and I'll talk about shortly. Instead of just using the correlation between a galaxy here and a galaxy here, or a galaxy here and a galaxy here, what I'm actually doing is counting all the gas that's illuminated by this background object. And I'm cross-correlating the overdensity of gas, specifically neutral hydrogen actually, with other overdensities of neutral hydrogen. So these are skewers of neutral hydrogen that are highlighted by the quasars in the background. And the specific way they highlight the neutral hydrogen is they trigger the Lyman alpha transition. So they trigger the 1 to 2 transition in neutral hydrogen. And that causes absorption in the spectrum because you're losing photons at that wavelength. And that shows up very clearly in our spectra. I'll show that shortly.
What is little r that goes from 0.5 to 5?
Okay, so little r here that goes from 0.5 to 5 is that's a version of co-moving distance that's not quite co-moving distance. Co-moving distance divided by 1 plus z, which looks like it looks like a luminosity distance. I'm actually not sure why I use that unit, to be honest with you, now I look at this. I've never actually thought about that unit, but so typically we say the Lyman alpha forest in co-moving coordinates, where you treat the universe as if you're not subject to light travel time, is about 12 gigaparsecs away, where a parsec is 3.3 light years.
So that's the same information as z, or is it different information?
It's translating z into some form of distance, but it's kind of a funny form of distance. It's not co-moving, which I don't know why we did that. But yeah, it's a form of distance. It's exactly the same as the information on the z-axis. And z is the direct observable. R is not the direct observable. Okay, so we have to be like 10 times bigger and faster than Sloan. Here's how we prepared our observations in Sloan. We had custom aluminum plates designed with a pattern of galaxies projected on them and holes drilled in a machine shop in University of Washington. We had a human being plug a fiber optic in each of those holes, day after day, week after week, year after year. And we had to do it for 20 years. So a human being plugged like 4 million fiber optics over the course of 20 years. And it's amazing. You had to talk about things like carpal tunnel syndrome. I mean, it mattered if you plugged it this way or from below. Like, we had to have a way of flipping the plates over upside down so people didn't get carpal tunnel. It's amazing. She was really good at it. She had worked as a dental hygienist before taking this job. And this was much easier on her wrists than working in the dentist office. She could do this in half an hour. I would take about 2 hours. And I would probably break, she could have to break no fibers year after year. I would break like a fiber every day.
Was she the only person doing this?
She was the most long-term sustained effort. Her name was Diana Holder. And there was a couple other people that rotated in and out with her. But we had one picture where we did 1 million in a month, and there was 3 people responsible for all 1 million. And we took their pictures with their hands up, all bandaged up. No, 100,000, not a million, 100,000 a month. I'm sorry, I lied. 100,000 in a month. But anyway, really a lot of work. We had to think about how to map them. It was a ton of work. What we do now is not only do we have a bigger mirror to collect photons faster, but we've gotten rid of the humans. So we now have a robotic positioner system that takes about 1 minute to reconfigure for a new field. There's 5,000 of these robots in here, so my survey speed is going to scale with two things: the collecting area of my telescope and the number of robots in my focal plane. That's going to tell me how much data I can collect. And those two things combined are about 10 times more powerful than what we had in Sloan. Okay, so that's where we get the factor of 10 in galaxy count, is these two things. There's more to it. This is the telescope. It's a Portmino telescope. The spectrographs cover basically the same wavelength range as your naked eye, a little bit further into the red, but they go 3,600 to 9,800 angstroms, and that's over 10 spectrographs. We collect one spectrum per fiber, one fiber per galaxy, and we do this over the years to get to 40 million, okay? I don't think I show many spectra, but you basically, from the spectrum, the main thing you want to deduce is the redshift. So you find lines that you can identify how much they're shifted and get the redshift of that object.
So this seems obvious, but so you already know where the galaxies are, I guess, from some other data set?
That's a really excellent question. So we know where the objects are in 2 dimensions, in angular coordinates, right? Our coordinates are right ascension and deck, but they look just like latitude and longitude on the Earth's surface. But we don't know their distance or their redshift. So by knowing where they are in 2 dimensions, we know exactly where they're going to be focused in the focal plane of the telescope, and that's where we put the robots. So it actually is not that obvious. You have to take into account the optics of the telescope and everything and know exactly where that object is going to be focused. And this fiber optic is 100 microns in diameter. Okay? So it's about the thickness of your hair, and you have to position it to 10 micron accuracy in this position to get the light down it correctly. The telescope's going to focus the light like this to hit that 100 micron target. So it's actually really amazing, and we have cameras set up to make sure everything's centered correctly and everything. Okay, so looking at the coverage, in 1 year, we finished taking data in June of 2021. June of 2022. And at the time, in June, I don't know the exact dates, but let's say June 10th, 2022, we took our last photon. And June 11th, 2022, the mountain caught on fire. And you may have seen this in the New York Times, you may have seen it elsewhere, but there was a huge fire that went over the top of Kitt Peak. We were shut down for about 4 months because of it. There was a lot of damage to the road, electricity. We wound up unscathed. But this is where we were before the fire. We covered a little more than 25% of what our design goal was in 1 year of a 5-year survey. So you can do the arithmetic, things were going great. And then the fire hit. But we're constantly maintaining a schedule that's ahead of pace from what's expected, even with other problems we've had. We've had cyber attacks, we've had instrument problems. We keep going faster than predicted. This just shows the redshift distribution of those different tracers. I don't think this is super important. But there are 4 different galaxy types and quasar types, as I told before. In total, this year 1 sample, without worrying what's on the figure, is 5.7 million galaxies. So already in 1 year, we've outpaced 20 years from the Sloan Sky Survey. So totally fantastic. Okay. 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 So here I can kind of go through things fairly quickly. My main point is just to say that we've done things well. We've learned from experience and done things better than we did in the last 20 years.
Just to help us think about it, what is the effective R of these spectrographs?
Oh, the effective resolution. Okay, so the resolution is effectively how well you can resolve wavelength as a function of wavelength. So our specific unit is like full width half max divided by central wavelength. And it ranges from 2,000 to 5,000. So on the blue side, it's about 2,000. And on the red side, it's about 5,000. And the main criteria are our ability to resolve skylines. I would say that's the most important thing, to be honest with you. to be able to separate skylines from the background. So the red is, you have more skylines than the red, so you have to have higher resolution in that regime. Okay, so our redshift precision is typically on the order of 50 kilometers per second, which is well below what's necessary for any cosmology constraints. That's much better than what's needed. Okay, so compared to previous programs, the only real program that's competitive is the Cylindrical Sky Survey. We're already bigger. We did a very special, maybe overly enhanced blinding strategy to make sure we could avoid confirmation bias. We never blinded the data in the Cylindrical Sky Survey. In DESI, we corrupted the catalogs in terms of the position of these galaxies, so no one could actually deduce what was the truth from the BAO precision. And that was done in a systematic way to allow us to avoid systematic bias in the measurements. Okay, this was the first time that was ever done at this level. This is just a detail of how that blinding was developed. Okay. We determined all the systematic errors before we unblinded. We did all the analysis configuration before we unblinded. We set the scales, et cetera, the methods, the technique, the theory. And we also developed those on mock catalogs. So we did a lot of that testing before we actually looked at the final results. We actually looked at the final results in December. So 5 months ago. We looked at it in real time at a collaboration meeting in Hawaii. Okay. I think for me the most interesting thing that we changed in this analysis was we really revisited the theory of this Baryon acoustic oscillation feature. You asked what's the theory motivation. It actually gets into real detail of how the baryons and the dark matter couple up, et cetera, and we really revisited that and translated the theory into systematic errors. And I think that was the primary change I've seen from the previous 10 years. Okay? And there's some other model changes. At the end of the day, we don't see any notable systematic errors in observational effects, in the choice of reconstruction, which I won't go into. It's an important technique to bring out more information from the data. In the choice of our assignment of error bars. We do find slight systematic errors in a few other terms. On the theory, as I mentioned, the theory is uncertain at the 0.1% level. So that kind of sets a floor on how well we can make these measurements. Remember, I showed those the WZ before, or the distance of function redshift before, and we're looking at like 2.5% fluctuation. So 0.1% is tiny. How galaxies sit in the halos. There's some uncertainty on how that couples to our modeling. I actually think this is exaggerated, but we're very conservative, and we put in a 0.2% effect. And then what we assume about the cosmology as we convert from observed coordinates to the coordinates we need for modeling, and some other things in the modeling space. But they're all pretty small. I think these are conservative. They're on the level of 0.25%. Okay. When I add these in quadrature to the statistical errors, all I'm doing is inflating the statistical errors by a factor of 1.05. So tiny, tiny, tiny effect on the overall precision. Okay. In terms of how well I'm able to measure this feature in all my redshift bins, it ranges from about a 4 sigma detection in the weakest cases, all the way up to almost a 10 sigma detection in the cases where I have the best completeness and the most survey volume for my tracer. And the aggregate precision with the systematic errors, adding all these distance measurements together, is about 0.5%. So that's how well I'm able to measure distances in the universe at this point, over all of cosmic history, 0.5%. Okay. One last comparison to Sloan. Those 2 decades of Sloan, it was about 0.6%. So we've already superseded Sloan in that dimension as well. And that's the one that matters the most, right? That's what sets the Hubble diagram. Okay, Now, that's galaxies and quasars. It's very intuitive. I'm just counting the probability relative to random of finding a pair separated by a distance. The other technique we use, what you asked about, was what are those colored terms in the quasars? That's the Lyman alpha forest. This is another probe of the underlying matter. And the idea here is that as a background quasar, shown as this purple pinkish point source, as its light travels to the observer through gases of neutral hydrogen, those gases of neutral hydrogen cause absorption through a triggering of the Lyman alpha emission line, or absorption line. So the 2-to-1 transition. That light is getting redshifted, so the different distances of the clouds get projected onto the spectrum at different wavelengths. So I get what looks like a forest. And if I look at the whole line of sight from the Lyman limit up to Lyman alpha, I see all this absorption from neutral hydrogen. I now have a map along the line of sight of neutral hydrogen. That neutral hydrogen traces matter just like galaxies do, so I can now do cross correlations, etc., get another BAO feature. Okay? This is what it looks like in a real quasar in the bottom. Okay, I'm going to skip this. But at the end of the day, we make the same BAO measurements. Here is what we see compared to Sloan in gray. The blue is what we get in DESI. The data are only correlated at the 10% level, so they're totally consistent with each other. This is in the two parameters, the distance perpendicular to the line of sight, distance parallel to the line of sight. Looks totally great, better precision with DESI compared to Sloan. And in combined, it's about a 1% precision measurement in this tracer alone. All the way out at the highest redshift. This is our most distant sample in DESI. So I want to kind of go through that quickly. I see one question, I'm happy to take others, but I want to get to the cosmology interpretation.
Yeah, I think this is great. I'm curious, do you have overlap between these different techniques for doing BAO so you can cross-check in between?
Okay, so the question is, what is the overlap between different tracers where we make the BAO measurements? And are we able to do cross-checks? So in DESI year 1, because our completeness was not 100%, and we really are in the early phases, we are pretty limited in our ability to do cross-checks. That Lyman alpha measurement actually has two different probes in it. One is Lyman alpha forest correlated with quasars, and one is Lyman alpha forest correlated with the Lyman alpha forest. So there you have a cross-check. This is the same redshift range, the same density field, exactly the same survey area, and they synced up very well. They actually gave the same results within the statistical precision. There was another one where two different types of galaxies overlapped. We didn't get quite enough completeness in the second class of galaxy to completely do a cross-check, but roughly speaking, we found consistent results, but I don't think it was a statistically meaningful test. It will be more statistically meaningful in year 3 and beyond when those completenesses go up, and then we're able to make very high confidence measurements in all the tracers. It's a detail, but our fiber assignment scheme favors one class of object over another, so we're not equally complete in all these different tracers. And the one that was the worst is the one that we couldn't really sync up that well with the LRGs, but we will in the future. Okay.
So you're saying that's why the LRGs are so discrepant with Boston and Boston?
Okay, so the LRGs have a little discrepancy with BOSS and EBOSS. It's something like a 2.5, at the same redshift bin, it's like a 2.5 sigma difference between the central values. Over all the redshift bins, if you hone in on that one, it's, I don't know, 20 or, I don't remember, it depends how you compute this. It's not very unlikely to happen. So it's actually not discrepant statistically speaking. It's also fairly uncorrelated. I think the correlation coefficient was about 20% between the two of them. So we see fluctuations between BOSS and EBOSS at the same redshifts. We'll do splits where you can really, in year 3 in DESI, we'll be able to do splits where we can really make sure they identify the same volume and are really tracing exactly the same matter. And there we can actually do a more like-to-like comparison for those splits.
Yeah, I guess I would have thought a lot of those are literally the same galaxies.
Okay, so Yeah, so oddly enough, it's actually a pretty small number. We can go into why. There's a lot, there's a lot of reasons. But one reason is just footprint. The BOSS footprint was preferentially at high declination, especially the eBOSS footprint was preferentially at high declination, and DESI was preferentially at low declination. So the overlap is actually not that high. The correlation coefficient is, I think, 20% between the samples. And there's another subtlety in that the imaging data we used for eBOSS in particular was really at the limits of what the imaging could provide. So there's a huge amount of scatter. So even though we defined things with a very similar color selection to what we did in DESI, because the imaging was so much noisier, things were scattering back and forth across that boundary. And there's a lot of galaxies in eBOSS that would not be observed in DESI because they're actually too faint when you get, or too blue when you get the real colors, or the higher precision colors that we have in DESI. So there's actually a lot of nuances. We've had this discussion within DESI. You're not alone. We haven't done the actual like-to-like comparison. I don't think it's going to be statistically meaningful. It's already at the limit. Like, you know, I took 14 measurements from DESI, and I took 14 measurements from BOSS and eBOSS, and I look at one here, and it's different by 2.5 sigma. That's basically what happened, right? And also, so it's not clear it's statistically meaningful. It's on the edge. I don't think it's meaningful. I'll show some other points to kind of address that in a second. So let's get to the cosmology. So first of all, what does the Hubble diagram look like? I showed the Hubble diagram from eBOSS. That was our final 20 years. Here I'm going to show it one tracer at a time. And I'm also going to overlay on the right where that particular tracer sits in these two parameters in a simple cosmological model. It's our standard model of lambda CDM, the parameters for those who are interested in omega matter, and something that's equivalent to the Hubble constant. Okay, it's an uncalibrated Hubble constant. So what we want is, if things are consistent, they should all overlap in this plane, right? And the scatter about the lambda CDM model is going to tell us how consistent we are with lambda CDM. So I add tracer to tracer to tracer to tracer. The scatter about lambda CDM is fairly small. And all of these overlap with each other. So this is one consistency check we do that's model dependent across the full redshift range of DESI. You can see the degeneracy direction changes because each tracer is coming in at a different redshift, but they all intersect. And that intersection is shown here in black as the combined constraint from all tracers. It really looks consistent with everything we see in DESI. At this level, we don't see any suspicious activity in the DESI data. Okay. The constraint we're able to make here is a constraint on omega matter of 5%. And we're going to start getting into some tensions, or possible tensions, with other probes in a second, because this is actually a little lower in a lambda CDM model than some of the other measurements are indicating. But everything looks consistent with DESI. Okay, we're also measuring the Hubble constant without any other probe at 1.3% precision. That's where we are in year one. Okay. So here's the way I prefer to look at your question. What does it look like when I take this combined DESI analysis in this lambda CDM model and compare it holistically to previous measurements? So we show it to our 20 years of Sloan measurements. The correlation coefficient is pretty small between these. It's something like 20 or 30%, and they're completely consistent. So holistically speaking, across the whole samples, I do not see anything significantly different between DESI and the past 20 years. If I superimpose the Planck CMB constraints in this model, also consistent. The degeneracy direction is very different, very small error bars, very high degeneracy between these two parameters. But also consistent. You can see that difference I was indicating about omega matter. The Planck data in pink is a little bit higher on the curve than the DESI data, and that leads to things like, some implications for our neutrino mass constraints, and also some of our dark energy constraints. Okay. When I combine with the Planck data, my 5% precision measurement of omega matter now turns into 1.6% precision, sorry. It's clearly dominated by the small error bars of those Planck data points, but this single epoch, the DESI helps resolve the degeneracy. Okay. So that's lambda CDM. We can stay in lambda CDM, and we can get into one of the tensions that's been reported in cosmology for many years, and that's that of the Hubble constant, where different measurements, depending on the technique, give different values of the Hubble constant. And then you have a debate. Is it fundamental physics, or is it systematic errors? So what I'm going to show is the one technique that relies on calibrating this BAO distance ruler from early universe physics, and then showing all the different permutations of data and what the derived Hubble parameter is, the Hubble constant. And the key thing that you need to do, this is a model-dependent statement, is you need to calibrate that R sub D term that I mentioned on the previous slide. I said H naught R sub D is my uncalibrated standard ruler. If I can get R sub D, I can figure out H naught. Okay? And R sub D, to get that in our standard model, just requires knowledge of the CMB temperature, the matter density, and the baryon density. So I need measurements that constrain those parameters. Okay? Omega matter gets nailed by the BAO. Omega baryon H squared, or omega baryon, the baryon density, can be done either by the CMB or by Big Bang nucleosynthesis. Okay? Okay? Once I get those, I can get constraints on H naught. And I would call this the sound horizon calibrated H naught measurement. I would call it the drag scale calibrated Hubble constant. A lot of people call it the CMB measurement of H naught, but that's really not accurate because it's not coming from the CMB physics, it's coming from the drag scale. Okay? So what do we get? If we don't use the CMB at all, and we just use Big Bang nucleosynthesis, we show what's here in the top figure. So consistent with like 68.5 kilometers per second per megaparsec. I can add in one feature from the CMB, that's the angular scale of the BAO feature, and it improves a little bit. I can show what we found in Sloan. Here's our Sloan measurement when combined with Big Bang nucleosynthesis. I can show what happens when you do the CMB without BAO. Okay? I get consistent results. I can open up, I don't have it here, but I can open up the expansion history and I still get consistent results. No matter what I do, no matter what data sets I use, if I use this sound horizon calibrated ruler, standard ruler, I get H naught of 68 kilometers per second per megaparsec, plus or minus a little bit. It's all consistent. Doesn't matter. Now, I'll leave it to you to decide. Okay? Here's the other technique with two of the primary measurements. The lower one is the one that's often referenced as the source of the Hubble constant tension. That's using Cepheid variables, supernova, parallax measurements, etc. So basically measuring things with basic geometric arguments locally and bootstrapping those out to supernova that are not too far away. That's shown over here. It's very discrepant from our early universe model. Another technique, which has an improved measurement that's not published yet, is this tip of the red giant branch technique. That typically comes in around 70. So I'll leave it to you to decide if there's tension. My only point is that if I use the early universe technique, calibrating the BAO feature scale, all the results are consistent. It doesn't matter what data sample I use, what model I use, blah, blah, blah. I get 68. So I think that's a key take-home message. Okay? Okay, now, let's get into dark energy. Go ahead.
What's your view of the recent claim that asymmetric neutrino background can relieve the Hubble tension, published a few months ago?
Okay, so there's a lot of measurements, or a lot of theories that claim to resolve the Hubble tension. My perspective is I don't know if there's a Hubble tension. I'm not sure if it's real or not. And the reason I say that is this measurement, the tip of the red giant branch, shows no tension. That's a local measurement, and it's consistent with what we find. So I don't know if there's a Hubble tension or not. There's a million ways to resolve it. If you resolve it, you also have to describe the CMB at really high precision. People struggle to do that. I am just not convinced it's real. I don't know. I don't know. What does anyone think? I mean, which measurement? It's exciting to look at this one. Depending on the day of the week, I think this one's right. I've changed my mind 10 times over in the last 5 years about this. So right now I'm feeling very agnostic about it. That's today's mood. Okay, so I hope that is a helpful answer to your question. Okay, but let's move into some other sources of tension that may or may not be real. So first of all, I talked about the equation of state for dark energy. I talked about it in a single free parameter where I just allow it to not be what Einstein predicted, but still be constant at all times. And if I look at the DESI measurements alone and constrain this, I get about a 15% constraint, 15% precision constraint on that W term. And it's completely consistent with that -1, which is Einstein's prediction. I can then throw in other data samples that also give me constraints on these matter densities, the redshift evolving equation of state, the redshift evolution of the distance measurements, okay, like supernova, the CMB. The CMB here is shown in pink. When I said before that the CMB is not a probe of H0, and that's because once you open up any flexibility of the expansion history, CMB can't tell what's the parameters describing the expansion history, what's the parameter describing H0, what else is happening. It just is a single epoch, and it can't resolve the degeneracies. You need the whole redshift relationship, the whole redshift distance relationship to really constrain it. This is one way of seeing that. There's a high degeneracy. Once I open up the expansion history, it can't differentiate W from omega matter, okay? It's a great, highly precise measurement, beautiful measurement, but it's at a single redshift. So you add in other things. The other 3 samples we include are supernova, and there's 3 different supernova samples. And this, in my mind, is the highest controversy in the latest results, is there's 3 supernova samples. The yellow and the green are highly covariant. They're largely the same supernova, analyzed by different teams. And there's a new sample that's based on photometric data from the DES survey, here denoted in black. We can combine our measurements with each of those individually. We cannot combine all 3 together. So we can just say A, B, or C are the result. If we look at this parameterization, everything's consistent. You add these all together and you get something that looks like W equals -1, no matter what supernova sample you use when you add in the CMB and the BAO. Okay, it's like to 3% precision. That's what's shown here. That's not shown here, I didn't include this, but it's a 3% precision measurement no matter what supernova I use. So we want to move beyond constant equation of state for dark energy. We want to let it evolve with time. There's a lot of different models that motivate that. This is the specific parameterization we use. There's 2 free parameters. DESI alone, because it doesn't have such a high significance measurement at low redshift, has a very high degeneracy between these 2 parameters. And it also runs up into a prior up against in the top right-hand corner of this figure. But you really see, it could be lambda CDM. It's totally consistent. It's within the 2 sigma error bars. Okay? When I combine it with the CMB data, I get what's shown in the pink. Now I have enough of a lever arm on redshift that I could start differentiating the time evolving parameters for the equation of state from the other parameters in my Friedmann equation. Okay? And it's the pink contours now at 2 sigma do not intersect with Einstein's cosmological constant. Specifically, they're discrepant at 2.6 sigma. So 2.6 sigma, we have a lot of debate about where things become exciting. Some of the tensions that have been reported in lensing with sigma 8 are about that level, or 2 sigma, and they've generated lots and lots of press, lots of paper following up. I don't know, who thinks 2.6 sigma is reason for excitement yet?
Excitement about what?
Okay, excitement about what? Oh, good question, good question. But excitement about showing that dark energy is something other than the cosmological constant, than what Einstein predicted.
Whether the dark energy is varying with time?
With varying with time, yes.
So what's
The fundamental thing is it what Einstein predicts, or is it something else?
Einstein doesn't predict any time.
Yeah.
It's either varying with time or it's not varying with time.
Yep.
Okay, so what,
Yep. So at 2.6 sigma, it is not varying with, it is varying with time. It's ruling out a constant equation of state at 2.6 sigma. So W is decreasing as I get to today. So W is less than -1 today. Or it's more positive than -1 today. I'll show that figure in a second.
I think operationally, we can say that 2.6 sigma is enough to stimulate the emission of any 30 vapors.
Yes. Yes. Totally. I wouldn't have been so excited, but what complicates things is you can add more data to it, and then you get a superposition of 3 different states. And the first state is the most conservative state. That's when we add this Pantheon supernova sample. That's the one that's been around the longest. Okay? We can then add the Union 3 sample, and you can already see the central values shift, and now the 2 sigma error bars are very clearly separated from lambda CDM. And then you can show the DES year 5 sample of supernova, and it's offset yet again. If I look at the precision of each of these in combination, when I add the Pantheon sample, it's 2.5 sigma discrepant from lambda CDM. If I add instead the unions, it's 3.5 sigma discrepant. And if I add DS year 5, it's 3.9 sigma discrepant. So it's a linear combination of these 3 states. I think we're all a little ambivalent about 2.5 sigma. How do you feel about 3.9 sigma?
How much do you trust the systematic errors on these measurements?
So in the BEO, awesome. Very, very little.
Yes.
Talk to the yeah. So I don't know the answer to that question. So what I would say is I think 3.9 sigma is definitely in the exciting range, but I don't know which of these is true, and it's like a linear combination of these 3 states. It's kind of a linear combination of the mundane with the borderline discovery of a new physics. So that's where we are today. Moving past those measurements, I can at least show what they look like and how W changes with time. You asked, what does it look like at low redshift? It really is, this is just a linear model. People also overinterpret this. This is just our simple 2-parameter model for a dark energy evolving with time. It doesn't necessarily have to cross -1. Most of the constraining power is probably coming from the left-hand part of this figure. But in that 2-parameter model, at local times redshift is equal to 0, it's looking a lot less like the cosmological constant and a lot more like something more like matter. So it would create less acceleration of the local universe. That's the direction that it's moving. And that general flavor is true no matter what combination I use. So I think that is an interesting statement. They all lie in the same plane. It's just the levels of tension with lambda CDM vary. Okay? But they all show the same general behavior. They also show the same general behaviors I showed early on with the Sloan data before I even came along with BAO. So you asked systematic error. I'm pretty confident in the BAO technique because we found it's almost exactly the same thing with a completely independent sample analyzed in a different way from a different telescope at a different time. So I'm pretty confident there. The supernova, they've done amazing work, but it's something in the analysis that leads to different results. And that's the level of the differences in analysis. Okay, so I'm going to wrap up. And I'm just going to quickly talk about neutrino mass. So neutrino mass is another interesting thing that factors into the expansion history.
And can I ask you a question on the previous slide?
Yes.
If you had a strong theory prior to W can't be less than -1, and you tried to put that in as a constraint on the analysis, can you answer what would happen to your sort of discrepancy from -1 as equation state?
Yeah, so we did not do this, but another group did. So they put in some specific models that don't allow that crossing. So like we call it like a thawing dark energy model. And instead of crossing, it just asymptotes to W equals -1 at high redshift. And they actually found, and these are single parameter models, and they basically found the same delta chi squared from lambda CDM as we found, the same levels of tension that we found. So their models are actually totally consistent with these, which to me, we didn't dive into this either, but it tells me that the constraining power is really here. That's where some of this information is coming from. And I'm not sure how the supernova are beating against the BAO. This is something that this is where I think people should do a little more investigation. And we're a big collaboration, and we're still trying to get other measurements out. And we're focused on the data. But it's super interesting question. Okay, so moving to the neutrino mass. If I look at the neutrino mass from CMB alone, I can see it in the lensing signal, I can see it in the omega matter signal, and I get a degeneracy between the neutrino mass on the y-axis and something on the x-axis that's going to be omega matter. In this case, I show H0. So I need some other technique at low redshift to resolve the degeneracy and put tighter constraints on the neutrino mass. Here, you can see as I go to higher values of H0, I'm going to get preferentially lower values on the sum of the 3 neutrino species. Our H0 constraint can nail this down from BAO. That's projected here in the pink. And you can now look at the cross section of the CMB data with our data, and you get an upper limit. It's a one-sided likelihood interval, right? We don't allow mass to go less than 0. That 95% upper bound is 72 millielectron volts, which is getting very close to the minimum mass allowed based on neutrino oscillation experiments. Part of it is the preferred central value as opposed to the precision. And there's some other work more recently that dives into that. My preference for diving into that is to look at the question of, how strict, where is this preference for what looks like a negative neutrino mass coming from? So I prefer to leave a little more flexibility to the expansion history. One can introduce other particles to the model, but if I open up the expansion history and I now float neutrino mass at the same time as I float these 2 parameters for the equation state for dark energy, W0 and WA, I actually find in the W0 WA plane, which is right here, the results actually look almost identical. So adding this extra free parameter does not change the significance of my time evolving equation state constraints.
Sorry if this is a basic question. Why does anything that you're looking at tell us about neutrino masses?
Yes. Can I get to that in a second? This is a super good question. I'll get to that in a second. So we find the same constraints, right? The gray is with a neutrino mass as a free parameter. The blue is without it as a free parameter. They look almost identical. So we don't lose any constraining power there. But what shifts is the 1D posterior on the sum of the neutrino mass species. So in red, it's what happens if I assume the expanding history is lambda CDM. What's in gray is now if I let it be flexible with the time evolving equation state, that central value that looked very negative before now shifts to be much more positive, and I get a much more physically behaved likelihood function. So it might be extra indication that there's something in my expansion history that allows my neutrino mass to contribute in a reasonable way. With just using the BAO and CMB, that upper limit is now about 200 millielectron volts at 95%. Now, the question is, how am I getting the neutrino mass in the first place? So neutrinos are almost as dense in the universe as the photons from the cosmic ray background. There's tons of relic neutrinos left over from early times in cosmic history. And because there's so many, their effect comes in 2 ways. One is it contributes to the overall energy density. So this omega matter actually has a neutrino. Well, at early times, when they're still relativistic because the temperature of the universe is hot, they're acting as a relativistic particle, and we can see that. As the universe expands, their wavelength increases, it gets redshifted, they become non-relativistic, that's around a redshift to 200, depending on their mass. And when they become non-relativistic, they act like mass particles. So that affects the transition from the CMB today in the expansion history. So that's one way it shows up. The other way it shows up, which is actually stronger, is because it transitions from being relativistic to non-relativistic, it affects the rate at which growth occurs. So it affects the amplitude of lensing from the CMB. So that also is where some of the CMB constraint comes from. So that's really where it comes in. But there's just a lot of neutrinos. So, and they affect growth of structure and expansion. And we can see that in the data at this level of precision. So we're actually, I mean, even with this flexible model, right, our 95% upper limit is 200 millielectron volts. That's far superior to what dedicated experiments to getting the absolute mass of the electron neutrino are getting, like the Katrina experiment, for example. So we're really sensitive to it because there's so many. Okay, so I'll wrap up. I think what I want the take-home message to be is, we can measure the Hubble constant to 1% precision in any combination of data sets or models. It's always around 68. We really see no evidence for curvature that's not zero, so a lot of times we don't allow curvature to float as a free parameter because it doesn't matter. There's some interesting behavior in the expansion history. It appears with the equation of state for dark energy when you allow W to not be constant and you allow some time evolving behavior. It's got a range of tension with lambda CDM from the relatively mundane to the super exciting. What we're hoping is that in the future, in the next year, we're hoping to get our next series of measurements out with Baryon acoustic oscillations, and we're hoping that that precision gets us closer to truth without the supernova samples, and we can get more clarity on what the real discrepancy with lambda CDM is. Okay? Otherwise, neutrino mass, also doing excellent. Depends on the assumption of the expansion history. I'll call it a day and take any last questions.
Thanks so much, Kyle. Let's see, time for questions.
I have a general question about the very negative value of the W.
Oh, of W. Oh, yeah, okay.
Of course, because it's a very high redshift, essentially the dark energy is not important.
Yes.
It's dominated by dark matter. How could you get such a good sensitivity of the area with this doesn't matter at all?
Okay, so it's a totally excellent question, and it's what I was alluding to a little bit, but maybe in not sufficient detail. So the question is, if I go to these high redshifts, my model tells me W is very, very negative, negative 1.5 for all these cases. How am I able to determine that if at those high redshifts, I'm deep in the matter-dominant regime, and the contributions from dark energy are fairly minimal. They're definitely way outnumbered by the contributions from mass. So my interpretation, and we haven't delved into this in gory detail, to my chagrin, I think if I have amazing constraints, let's look at an extreme case. So I have amazing constraints between redshift 0 and 0.5, and I have no data out here. And I fit a linear model to that. That linear model, when I extrapolate it all the way out to redshift 2.5, it's got a cross. And it doesn't mean I'm constraining it out there. It's just an extrapolation from where the data are actually being constrained. My suspicion, so our pivot redshift is around right here. I think that's where the constraints are the strongest. And my feeling is this is all extrapolation based on the analytic form of the model we're using. But we have not shown that, and I don't know.
Instead of 1 minus A, it could be 1 minus square root of A.
It could be 1 minus square root of A.
Yeah.
You could also, I mean, as I alluded to, another group used a different model that wasn't any of this. It was asymptotically approaching W equals minus 1, and they found roughly the same degree of tension with lambda CDM that we're finding. So I think it's indication that in my view, a lot of the constraining power is coming from how they all play together at low redshift.
Yeah, I agree with that.
But it's hard to know for sure.
You showed basically, if I was nervous, then the two LRG bins might be driving the preference away from the cosmological constant, the preference for low mega matter, high H naught, and overly tight and new. What could have gone wrong in the LRG bins, or is there really nothing that could have changed?
Okay, so I don't know. Do I ever show? Let me see if I can. Okay. So the question is the LRG bins. This isn't the full dimension. So this purple curve here and the orange curve here. The orange curve is slightly discrepant from lambda CM. A lot of people have been asking how much of our constraining power is coming from that orange bin. Why is that? Is that what's driving our negative neutrino mass? Is that what's driving our time evolving equation of state? That is something like a 2 sigma deviation from lambda CDM. It is at a sweet spot for time evolving equation of state. However, I will tell you a couple of things. You know, fluctuations happen. If I take away all these redshifts, all of them, throw them all in the trash, I go back to what we did in BOSS and EBOSS, I get the same result. I get the same negative neutrino mass, I get the same W naught WA, I get all the same results.
Maybe there was something about one versus both bins being correct, but just for the sake of argument, I believe those fluctuations were systematic. Is there something that could explain it, or is it really,
So, I mean, we found nothing. What could possibly explain it? So first of all, it would have to be unique to that bin and not to the other bins. We measured everything exactly the same way. It was observed at the same time, all the same pipeline. The data are actually higher quality than this blue here because it's more complete. So it has to be something unique to that bin, and I don't know anything that's unique about it. The things I could imagine we would do a little bit differently in year 3 are really subtle changes, like maybe at the 0.1% level. I think we had a fairly simple reconstruction assumption. We just did everything across one large redshift bin between 0.4 and 1.1, but I think it's only a 0.1% effect. We don't see anything in the systematics weight. We turned off the systematics completely and don't see, the imaging systematics, and don't see a shift in the central value, so we know it's not imaging. There's nothing I know of that I can point to that would drive this fluctuation besides statistical. So what I would like to do in year 3 is take all these measurements while still blinded and split each of the samples in half, not in area, but in like luminosity. So you get exactly the same volume probed by different samples, and I would like to cross-correlate them and see if there's any subtleties there. We did not do that in year 1, and we can do that in the future. That's something that would be nice to do. But I don't know of anything that would be different about that interval, that redshift bin, than the rest. A lot of people have brought attention to this, even people in DESI, so I'm not just saying it's the peanut gallery outside throwing things at us. I don't believe any of it. So, but we'll revisit it with better statistical data in year 3.
All right, last question from Bernie.
As a follow-up to your answer, what other additional things would you do in year 3 analysis to, overcome this kind of tension?
Yeah. Okay, so improvements, so we'll do it all blinded. The improvements we're talking about doing is a more redshift dependent reconstruction, which I didn't go into here. A different way of dealing with fiber incompleteness, the incompleteness in the fiber assignments. I didn't go into that here either. We actually can we can actually statistically recover all the fiber assignments through this technique called pairwise inverse probability weighting. And then you actually just count the probabilities, not that an object gets a fiber, that a pair of objects gets a fiber. So we'll introduce that in year 3. We may do different slicing in the redshift intervals, but I don't really see any huge changes. The only big change that could happen that I don't anticipate is we'll go from an analytic form for determining the error bars to a purely empirical form based on mocks, but I don't actually see that happening in the time scale that we want for year 3. So there's nothing I see that's suspicious, and we also we did everything all over, but we were able to reproduce with these techniques what we saw in BOSS and EBOSS on the BOSS and EBOSS data without much difference from BOSS and EBOSS. So even though we visited everything, we got the same results there too. So there's nothing I see that indicates this is not statistical.
All right, let's thank Kyle again.